Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're going to be going through the problems and solutions from Chapter 2 of the SOA recommended LTAM multiple choice problem list. If you're looking at this as part of the LTAM course, again, I suggest that you try these on your own, and if you get stuck, watch the video enough to get unstuck based on how I walk through the solution, and then try to finish it up on your own. Also, I highly recommend going through these problems in order, as these are a sequence of problems on the same material, rather than taking the time to explain in all the detail the same solution procedures again and again. I may say after the second or third time that you go through a procedure, I'll say, yeah, we've seen this before, it's just like something from a previous problem. So I recommend going through these in order. With all that out of the way, let's start with problem 1. This is one where you were given the survival function, and it was a survival function of this form, 1 minus t over omega to the 1/4, and they give you the force of mortality at age 65, and you have to calculate the current expectation of life at age 106. So first thing that you do is you find omega. You find that age which, according to this model, it's impossible to live past. And the way you do that is we use the formula that the force of mortality equals negative derivative log survival. So they give us the survival function. We do our calculus of negative derivative log survival. And we get that since they told us force of mortality at age 65 is 1 over 180, algebra happens and we get that omega equals 110. Okay. What this means is that it's impossible to live past 110, and if you crunch your numbers into your survival function, suppose you pick a radix of 10,000. Let's assume that we started with 10,000 people. Doing the algebra on this, according to this model, 4,367 would survive to age 106, 4,064 would survive to age 107, 3672 would survive to age 108, and 3088 would survive to age 109. Now, this obviously is a rather optimistic survival function in that such a large portion of the population live to within 1 year of the maximum possible age. This is a rather extreme case of what gets called the rectangularization of life, but okay, we'll just go with whatever they told us. So, 4,367 people survived to age 106, and then from that point onward, those people would have a combined 10,824 more birthdays between them. And just add up. 4064 to age 107, 3672 to age 108, and 3088 to age 109. Divide the 10,824 by 4367, you get a current expectation of life of 2.48 years, which rounds to 2.5, which was one of the answer choices. It's worth noting that suppose that instead of asking for a current expectation of life for a 106-year-old, suppose they asked for a 90-year-old. Then, yeah, that would be an awful lot of arithmetic to do. They would not ask you to do that by hand. There is an approximation technique they could ask you to do. And in the next video, I'll walk through how to do that. But that's problem 1. Oh, and of course, so I kind of logicked through all of this. For those of you who prefer algebraic formulas, you can say current expectation of life of 106 is survival of 107 plus survival of 108 plus survival of 109 all over survival of 106. So that's the formula. And you just keep adding up until you run out of stuff to add. Since it's impossible to survive past your 110th birthday according to this model, we don't have to worry about survival of 110. Yeah, that's the formula. You could either try to commit this formula to memory or just logically make sense of the procedure. But yeah, that's problem 2.1. Problem 2.2. This one feels strangely relevant given recent events. Scientists are searching for a vaccine for a disease, and you're given the total number of lives exposed to the disease. You're told that probability of survival in the first year is 98%. Well, I guess they tell you probability of death in the first year is 2%, but you can infer probability of survival is 98%. And then if the vaccine is ready, probability of survival in the second year will be 99%. And if it's not, then it will be 98%. Probability of the vaccine being ready will be 0.2, 20%. And it wants a standard deviation of the number of survivors at the end of year 2. The key to this problem is understanding how to interpret these Q probabilities. I just said these are death probabilities, so one minus that is a survival probability, as well as remembering from exam P the law of total variance formula, or the conditional variance formula. So if we let X be the number of survivors and V be 1 if it's developed, and if the vaccine is developed, and 0 otherwise, variation of X equals variation of the expectation of X for a given V plus the expectation of the variance of X given V. So variance of the expectation of X for a given V. Notice that expectation of X will either be, if you crunch the numbers out, it will either be 97,020 or 96,040. If you crunch the numbers out and say either the vaccine will be ready, in which case expected number of survivors would be 10,000 times 0.99 times 0.98, then you get 97,020. Or if the vaccine is not ready, you'd get 10,000 times 0.98 times 0.98, or 96,040. And if you remember your formula for variance of a binary variable, right, something that can only take one of two values, it's probability of it's taking the first variable, or the first value, times probability of it's taking the other value, times the square of the distance between those values. And that gets you 153,700. Then, the expectation of the variance of X is, so there's a 20% chance that the expectation of the variance of X will be, there's a 20% chance that the variance of X will be 100,000 times 0.9702 times 0.298, right? I'm just using the formula for variance of a binomial distribution, and an 80% chance that it'll be similar with a different success probability of 0.9604, and so failure probability of 0.0396. Do the arithmetic, you get that the expectation of the variance of X is 3620, so total variance is just the sum of these two, which would be 157,320. I just realized there's a typo in here, missing some zeros here, but this number is correct. And the standard deviation of X would just be the square root of the variance. My apologies for the typo. Problem 3. You're given that mortality follows Gompert's law, and they give you the B and the C. Remember that for Gompert's law, we always assume A equals 0. Gompert's law is a special case of Macon's law with A equals 0. And you're supposed to calculate the probability that a 50-year-old will die in exactly 10 years. The probability density of that. So, looking up in page 6 of the LTAM tables, they give you force of mortality of X and survival probability of X and T for Macon's law. You just set A equals 0, B equals 0.00027, C equals 1.1. We also use the fact that the probability density of surviving 10 years starting at age 50 is the probability of surviving the 10 years and then dying. So this probability density is you have to survive up until then and then die. You just crunch the numbers in and you get 0.048, which is one of the choices. So again, use the formulas that they give you on page 6 of the tables, plug the numbers in, and just get the answer. Problem 2.4. You're given the probability that a newborn dies within t years is t squared over 10,000 for t between 0 and 100. Calculate the complete expectation of life of 75 colon angle 10. So, what we can say is, since the colon angle 10 means we're only concerned with 10 years from now, we can take the integral from age 75 to age 85 of s of t dt over s75. Another way of explaining it is having this colon angle 10. Suppose that exactly 10 years from now there will be some cataclysmic event that will kill everybody. Dark, I know, but mathematically it works. What that means is that 10 years from now, the printed survival function that we had would be wrong. Due to the cataclysmic event, we'd say that s sub 0 of 85 would be 0 because of the cataclysm. And so you'd integrate the regular survival function for the first 10 years and then integrate 0 afterward. And integral of 0 is just 0. So you plug in the survival function. You plug in the survival function at 75. Do the calculation, you get 8.21. 2.5. You're given E40 colon angle 20, E60, 20Q40, and Q60. And you have to calculate the curtate expectation of life of a 41-year-old. This problem relies on using the two recursive equations, a single-year recursion and a multi-year recursion, for curtate expectation of life. And the strategy is we want to calculate curtate expectation at age 40. We can do that given probability of surviving 20 years and E40 colon angle 20, I guess, and E60. Sorry, this is Q40, not Q60. I misread it at first. But then to go from E40 to E41, we use a one-year recursion. And so going through that in more detail. So noticing the 40s and the 20s, we realize 40 is probably going to be an important number. Using the one-year recursion formula, we have E40, which we don't have, equals 0 times Q40, plus 1 plus E41, which we're looking for, times P40. We know that Q40 is 0.003 and P40 is 0.997. But this one formula has two unknowns, the E41 that we're looking for and the E40. That means we should probably solve for E40 first and use that to solve for E41. Fortunately, we have the recursive formula for that. E40 equals E40 colon angle 20 plus 20P40 times E60. We crunch the numbers, we get E40 is 38. Plug that back into this formula up here, and algebra happens, we get E41 is 37.1. So this problem relied on the two recursive formulas, the single-year recursion and the multi-year recursion. Problem 6. You're given a survival function and asked to find the force of mortality. Well, 1,000 times the force of mortality, but you can find the force of mortality and then multiply by 1,000. So, fortunately, this is a simple enough problem. Force of mortality equals negative derivative log survival. They gave you the survival, do negative derivative log survival, you get that it's 0.0133, multiply by 1,000 and you'll get 13.3. Okay. That was probably the easiest problem on the whole set. 2.7. Well, no, maybe this was the easiest problem. They give you a survival function, and they say calculate the probability that a 30-year-old dies within the next 20 years. So I just assumed a radix here. I assumed a starting population of 1,000. On average, 880 would survive to age 30, 750 would survive to age 50. And you just plug into your survival function and you get those numbers. That means that between so of the 880 who survived to age 30, 130 would die out of those 880, which gets you a death probability of 14.8%, or a survival probability of 85.2%. For those of you who like the algebraic formulas, here's the algebraic formula. 20q30 equals s of 30 minus s of 20 plus 30 divided by s of 30. Or in other words, number who survived up till that point minus number who survived later, that gets you the number who died in between, divided by the number who survived at the start. And finally, 2.8. In a population initially consisting of 75% females and 25% males, you're given for a female, the force of mortality is constant and equals mu. For a male, it's constant and equals 1.5 mu, and after 20 years, the population consists of 85% females and 15% males. Calculate the probability that a female survives 1 year. Here I just assumed an initial population size of 400. And I said that if f is the number of females after 20 years and m is the number of males after 20 years, we'll have f of 20 equals 300 e to the negative 20 mu, and m of 20 equals 100 e to the negative 30 mu. F of 20 over m of 20 equals 85 over 15 because of the 85 to 15% ratio that they gave us at first. Crunching the numbers, just dividing one by the other, we get 3e to the 10 mu equals 85 over 15. Doing the algebra to solve for mu, we get mu equals 0.0636. And survival probability for a female, p sub f, is going to be e to the negative mu. So we get 0.938. And that concludes the problem list, or the problem set and solutions to the problem set from Chapter 2. It's a relatively short problem set. The others will be longer. But as always, if you like the way I explain things and want to arrange private lessons, click the link in the description below. Until next time, this is Dr. Nighttime wishing you a good night.